Hello everyone, and welcome to today's webinar, GPS/GNSS and Cybersecurity, brought to you by GPS World Magazine and our sponsor, Microsemi. I'm Joelle Harms from North Coast Media, Senior Digital Editor for GPS World, and I will be your event manager. Before we get started, I want to let you know today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and also will be emailed to you tomorrow. At this time, I'd like to acquaint you with the ways you can participate during today's presentation. Please notice the Submit button in the lower left-hand corner of your console. If you have a question, please type in the text box at the bottom left and click Submit to place your question in queue. We encourage you to ask questions throughout the presentation. We will address these questions at the end of the presentation during the Q&A portion. If you experience any technical difficulties during today's event, you may also use the Q&A box to submit your issue, and Assistant Producer Bethany Chambers or I will personally assist you. GPS World's Twitter feed is placed on the right side of your screen. You can use the hashtag GPSWorldWebinar to submit any questions during today's webinar or to enter into discussions with other attendees. You can learn more about our speakers and moderator by viewing their photos, bios, email addresses, and Twitter handles, which is located in the upper left-hand corner of your console. If you're logged into your social media accounts, you can share the webinar's title, description, and URL with your friends or colleagues on popular social media sites, and that's within the Share This widget. Now I'd like to turn today's event over to our moderator and GPS World's publisher and editor-in-chief, Alan Cameron.
Thanks very much, Joelle. And hello, everyone. Welcome to this webinar on GNSS and cybersecurity. I see we have participation from many parts of the world. I'm going to get out of the way as soon as possible. First, I just want to say thanks again to our sponsor, Microsemi. You'll be hearing from Microsemi as part of this webinar. We have 4 speakers coming at this rather broad and fascinating and vital, increasingly vital in these times, topic. Each one will speak on a different subtopic, a different angle of perspective. We'll hear about authenticatable signals for anti-spoof and proof of location, then securing network time services, the next generation of NTP technology. We'll take a general system perspective on GNSS security, and finally, improving GNSS receiver security via signal processing and sensor fusion. I'll return between speakers and return at the end after all 4 to pose some of the questions that you have submitted both in registering for the webinar and any that may occur to you during the course of the presentations. Right now, let's go directly to Logan Scott, consulting engineer and principal of Logan Scott Consulting, LSC. Logan, you're going to talk about authenticatable signals for anti-spoof and proof of location. Take it away.
Well, thank you for the introduction there, Alan. So basically, I'm going to talk a little bit about securing position and time in virtual space. And the thing I want to really get across here is that this is not just a receiver type of problem. So I start with an operational definition of spoofing. And basically, I would argue that spoofing is a process where someone or something tries to control reported position out of a device. Now, it's important to understand that this can be incorrect PVT from a local user, in other words, my local receiver, or in my reports to an asset tracker or some other device out there. And it's important to understand that spoofing is not of necessity an RF attack. The one that garners all the headlines is the stuff that Todd Humphreys has done and the young Chinese lady at DEF CON. But it's important to understand that there's a whole attack surface associated with non-RF attacks. And basically, these are lying types of attacks where you become the location object and you lie about position. Now, just as an example of this, if we were to look at Pokemon Go, there's 2 methods to spoof this, method 1 and method 2. And method 1, you root your phone, then you install something to hide the fact that you're rooting the phone, and then you install a fake location spoofer. And as you can see from the installation numbers, this type of spoofing has become quite popular in the last 2-3 years. The alternative is to go off and do something like an RF spoofing attack. But as you can see, this is a fairly complex attack and requires a lot of effort. Now, this is becoming an increasingly easy style of attack to launch, but it is important to understand that if you can cyber spoof, you're much more likely to do that, given that it's much easier. Okay, so whenever we talk about spoofing, we need to ask, well, why would someone do that? Without motivation, someone's not going to do that. And I think one of the most important ones is to fool asset trackers without raising alarm. In other words, where is that container? Or if we're talking about pay-as-you-go insurance and road taxes, how do we fool these systems to avoid those taxes? If we look at illegal fishing, about 1 in 5 commercially caught fish right now is caught illegally, and it's a $24 billion market. So there is evidence of spoofing going on in those fields, and mostly of a cyber variety. Another thing to understand is that a lot of crowdsourced databases have a location component in them. Whenever you talk about parking, traffic, the FAA's next-gen system, and so on, there is a location component. And so if I can create a mobile botnet, I can also lie about location and create some really interesting effects. In other words, I can say all the parking spots are taken at a place, and then I go in there and have no problems with parking. And then finally, we can look at bypassing geofences. A lot of drones are now geo-restricted as to where they can operate. But also, if I've got a geofence truck, say an almond truck, carrying $180,000 worth of almonds, then one of the things I can do is hijack that using some kind of a spoofing technique. But again, understand that the attack surface includes both RF as well as cyber methods there. Okay, so there's a lot of techniques you can use in a receiver, and I'm not going to go through these in any detail, but I do want to observe the following, that even if you do all of these techniques here, you need to keep in mind that receivers are computers and they are subject to cyber attack, and so you can invalidate most of these techniques just by lying. In other words, putting bad software load in there or some other technique. Okay. So whenever we talk about location reports, we always have to ask, how do we know he isn't lying? Again, spoofing is not just about RF. Okay, so one of the things I've been arguing for many years now is that we need to have authenticatable civil signals, and this is needed both for anti-spoof as well as proof of location. So when I talk about anti-spoof, that's basically spoofing the receiver and spoofing the location that I think I'm at. But I'm here in Fort Collins, and if I wanted to prove that I'm at a particular location, I would need some method for proof of location, and you would need some method for verifying the receiver. In other words, detecting any lies that I might be telling there. Now, there's a lot of different approaches that are possible here, but I'm going to talk about GPS RF signal structures, and there are some other things that can be done as well. And finally, I should note that this needs to be operable on untrusted hardware. In other words, you can't necessarily trust the hardware at the other end in a proof of location type of scheme there. Okay, so one approach for doing this is we can watermark the signals using a watermark generating key, which is basically a cryptographic key which creates a seed value going into a cipher stream generator. And then what we do is we generate a spread spectrum security code, and we insert that into the signal, basically using a puncturing method, in a time-hopped pattern there. You might say, well, obviously I could receive both of these signals, so how does this watermark signal? Well, the trick is this. The watermark generating key changes periodically, say once every 3 minutes, and then what we do is we publish the watermark keys with a delay. So you might always have a 3-minute delay there. So the control segment and the space segment would know what the keys are in real time, but as far as the user is concerned, he wouldn't know what these are in time. And so this can be used to verify the signal came from a satellite as follows. Basically, we track the signal as usual, plus we collect the pre-correlation A to D samples. Now, the reason we can track the signal as usual is because we've only done a 10% watermark here, and so there's a loss of about 0.9 dB in signal-to-noise ratio. But other than that, everything seems to work quite normally. So we collect these pre-correlation A to D samples, and then when the watermark generating key becomes available, say 3 minutes later, then what we do is we generate the spread spectrum security code. We despread the collected A to D samples to look for that watermark signal, and if we don't detect a correlation on that spread spectrum security code, we can say that the watermark is not there, and so we don't validate the signal. So what that does is it stops people like this from operating because she has no way of knowing what the watermarks are in real time. Similarly, it would stop a Todd Humphrey style spoofer because he doesn't know what the watermarks are in real time. Okay, so one of the other uses for authenticatable signals is to prove locations to remote sites. And so as an example, in the top right, you see a generator. It's a 5,000 horsepower generator that was connected to the internet. This was a DHS experiment conducted a few years ago. And basically what they said is, can you break the security and gain access to this and then input commands that will cause this thing to self-destruct? And so about an hour later, you see the smoke coming out of it. And basically what they did was they took the load and they hooked it up full load, no load, full load, no load. And by doing this back and forth, they created a lot of mechanical stress on the system and basically caused it to break. Similarly, we'd like to know where containers are. This particular container showed up in Genoa, Italy, and it was labeled scrap metal, but one of those pieces of scrap metal was made out of cesium-60, and so if you stood next to this thing, you would have got about 360 chest x-rays per hour, radiation equivalent. And then finally, we need to be able to verify the location of receivers that are reporting positions to us. In essence, lie detection. So even though it might be a cyber attack, if you use RF techniques, you can detect the lie in the cyber thing. And it's quite difficult for the cyber attacker to create a valid location signature. Okay, so how do we do this? Well, basically, if you have authenticatable GNSS signals coming in, you go into an A to D conversion process, and then you send those samples over to what I call a location authentication object before the watermark generating keys are published. Then when those keys become available, we can combine that with ephemeris, and which is basically telling me where the satellites are, and establish what the location is of that device. Remember, you always navigate the antenna, and so this location authentication object does not have any RF capabilities because it's using the A to D samples from, for instance, that container in the top left. Okay, in terms of the location signature size, anywhere from about 125 to 500 kilobytes would be appropriate. Again, these are raw A to D samples. So, stated another way, about a quarter of a JPEG image taken by your camera. So it's not a huge amount of data that you have to transfer around in order to prove location there. Okay, so how can you use this in a practical environment? Well, here's an example where I've got a cell phone, and I've also inserted a micro SD device in here. And what this can do is accept the raw A to D samples, again, before the watermark generating key is published. And then when we get the watermark generating key, perhaps from the phone, there are ways to authenticate that key, we can then establish whether the phone's location is the same as what's coming in from those A to D samples by checking the watermarks. And in fact, one of the things you can also do with that phone is send it off to a remote location authentication object. Again, these things are just software. And so what this does is it gives you a security model where you can watch the watchers. In other words, you can watch not only the phone, but you can watch that thing labeled Crypto Vault. Okay, so you can certainly get better location verification and validation using this kind of approach. And just to give you another example, essentially the same model, here I've put it into an aircraft, and basically what I've got is this Crypto Vault device is verifying the location of the aircraft, but also the aircraft is sending down some of those raw A to D samples to a location object, I should say a location authentication object, and we can establish that the airplane is at a particular location and altitude. And similarly, the control tower could also send up location signatures, which is basically raw A to D samples, send those up to the aircraft, and the aircraft can then verify where the control tower is. In other words, he's getting commands from an authorized location. And you might say, why do I need something like that? Well, here's an example. Basically, what these folks did was they created a bunch of ADS-B signals using a USRP, which is basically a software-defined radio. And in this chart, all of the white ones are fake aircraft. The blue one and the yellow ones are real aircraft. And what you can see from this is they basically flooded the system with a bunch of ghost aircraft. Now, if I had to prove location, one of the things I'd have to be is at an altitude of, say, 32,000 feet. Well, that's not necessarily an easy location to go up to. And so you can eliminate a lot of this type of spoofing by using location signatures and authenticated signals. Okay, so just in closing here, I want to make a few remarks here. One, location provides a security context, and it's an important attribute of your identity. You can't be in two places at one time, but on the internet you can be. And so one of the things that proof of location can do for you is it can create that unique identity attribute, and it can also provide the security context saying you're within the perimeter of a fence versus outside of the perimeter. There are diverse motivations for civil spoofing, and it's becoming easier all the time. You can get spoofers on GitHub now. All you need is an SDR. And because of that, I think we can expect more attacks. There's financial motivation, and it's getting easier to do. I would also note, and again reinforce, that both RF and cyber techniques have to be defended against. If you defend against one and ignore the other, you still have a major attack surface available. And then finally, I would say that civil signals need to be authenticatable at the chip level. James Kern is going to talk a little bit more about this, I think. But if you say we're going to authenticate the 50 bit per second data, that's a partial solution. It's an important element of the solution. But it can also lead to overconfidence, because if you authenticate the data but not authenticate at the chip level, you don't necessarily know that you've got a true range. So with that, I'm going to turn it back over to Alan and let him continue here.
Thank you, Logan. And we'll come back later to any questions about Logan's presentation. Right now, we're going to hear from Paul Skoog of Microsemi, who's going to talk about network time protocols and securing network time services. Paul?
Great, thank you, Alan. And let me cue up the slide here. First off, I'd just like to thank everybody for their time today. I appreciate it, and I'm hoping over the next 10 minutes or so, I can help you make a practical connection between GPS and cybersecurity. So with that, I'd first like to make a connection about Microsemi and cybersecurity. You may not be aware of this, but we're a global provider of synchronization solutions and a leading supplier of timing infrastructure. And I bring this up because we manufacture atomic clocks. These are going to be cesiums and maser atomic clocks that contribute to what is known as UTC, Universal Time Coordinated. And what's important about that is that every server, workstation, router, and so forth, networking equipment that uses time is referenced to UTC, Universal Time Coordinated. So you find that UTC is vital, essentially, in a role in cybersecurity. And so let me continue to make that connection for you. We'll go to the next slide. So if we just kind of step back and we look at the three GPS segments, we have the control segment that has atomic clocks in it. We have the space segment with atomic clocks on board in every GPS satellite. And then, of course, there's the user segment, which we're quite familiar with. And in particular, there's a timing aspect, a whole industry around timing and using time that we get from those atomic clocks. And that feeds into critical infrastructure, not the least of which is computer network operations, stock trading, financial things, SATCOM, and so forth. And so since we're talking about cybersecurity, which is a networking topic, we're going to drill in on computer network operations. Okay, so a key slide here, the role of timing in cybersecurity. So just on a side note, when I talk to operators of IT networks and we talk about time synchronization on the networks, I ask them what the most important reason to synchronize the time is, and they tell me almost 100% of the time it has to do with log file timestamps. And so why would that be, right? Well, log file timestamp accuracy is absolutely critical in the role to defend against cyber attacks, mainly because the logs are generated by all the servers and all the activity that they do and who logs in when and where and does what. So essentially it's the footprint, the fingerprint, the trail that gets left behind is in the logs, right? And so there are products out there originally targeted at large enterprises, but now they're available in medium and small enterprises, and they're called SIMs. Security Information and Event Management applications, and they aggregate the logs from all the servers, from around the planet, if you will, into a single location, and in near real time analyze those, looking for any kind of security breach so they can have a quick defensive action, right? So a lot of active monitoring going on here. The only way to really make sense of those logs is if they're all on the same time base, no local different time zone issues come into play. UTC is that underlying time scale that gets used by these particular systems. So to put this in a real-world example, I imagine most of us have a credit card, and MasterCard and Visa and so forth, and they're all part of the payment card industry, which has a data security standard. And if you look in that standard, in no uncertain terms, they require time synchronization, specifically for the purpose that they have to compare logs between different systems to establish, exact sequence of events, right, for forensic purposes. So clearly, time and log files and cybersecurity detection and prevention are just completely linked. So if we sort of connect the dots here between GPS and networking, you can kind of get the idea. GPS is a wonderful source for accurate and reliable UTC time planet-wide. Then we have the network infrastructure there. It consumes UTC. It needs it to be reliable and accurate. It uses the network time protocol to distribute that time. And so standing in the gap is a GPS referenced NTP network time server, right? Synchronize the GPS and provides the NTP to the infrastructure. Well, GPS is subject to jamming. In the recent issue of GPS World, they cited in a survey that GPS jamming, when you combine intentional and unintentional sources, is one of the top 3 issues concerning GPS in 2016. And then we look over what's happening in the network infrastructure side, and Akamai Technologies is, telling us that NTP is considered one of the most vulnerable network services and has one of the fastest growth trends as a DOS target. So here's the GPS referenced NTP time server coming under attack from the GPS side as well as the network side. So how do we address that? So since it has to do with the time server, I'm going to use a microsemi product. It's a Sync Server S600. It's an GPS referenced NTP time server, so I'm going to use that for the context of the conversation here. So let's first start with jamming and the effect of jamming on a time server. If you consider the blue box being a time server, inside it has a GPS receiver, and the outputs from the receiver go into a timing loop that ultimately disciplines a local oscillator, right? And off a local oscillator, we get NTP timing information that provides to the infrastructure. So what happens in a jamming event is effectively the same as unplugging the antenna to the GPS receiver. It gets swamped. It can't track the satellites anymore. It goes into an unlock condition. So in the time server, if it sees a GPS unlock, it goes into a condition that we call holdover. And essentially, it's flywheeling. It's just the local oscillator is no longer being steered, and so it's just flywheeling along. Now, of course, we notify the administrator that there's a problem, but we still want to continue to provide accurate time services to the network. So the solution to that for jamming essentially starts with first an accurate clock. A clock like this Sync server is accurate to about 15 nanoseconds RMS to UTC. So it's a great source of UTC time to those cybersecurity systems and their log files. But if you have a jamming event, you're going to lose GPS and you're going to holdover. And now you're on that local oscillator. And in the table, you can see how much that oscillator will drift in a 24-hour period. And so the best defense against jamming is to put in a very good oscillator. In our case, we recommend a rubidium. It's a miniature atomic clock. They're a fairly small rubidium-based device. They're relatively inexpensive. But there's 2 really big advantages that this provides. And one is you can see that the drift is merely microseconds a day. It's very low. So for NTP distributing NTP distributing UTC, very accurate, stable source of time. So that's one key advantage. The next is it buys the IT guy who's managing that time server time to figure out where the jamming's coming from. So great holdover off a rubidium oscillator. What about on the networking side, right? What are our problems that we have there? Well, that gets into NTP, attacks on NTP time servers, right? And so why would that be? Why are they such an attractive target? And the types of attacks they're exposed to are denial of service attacks, NTP amplification using spoofed addresses. That's where you can send a small packet to the server and it responds with a whole ton of data. So it's a nice amplification effect. Well, why does that happen, right? Well, fundamentally, there's a lot of publicly available time servers out there. If you look down there under the reliability line, you can see that our friends at ntp.org, their time servers in that pool are being accessed by millions or tens of millions of systems around the world, including the hackers, right? And they're, even need more servers. Well, NTP time servers use UDP. It's connectionless. The data is sent in the clear. It's reasonably easy to spoof. And so it's just a vulnerable, easy target to start with when it comes to a cybersecurity attack. So from our standpoint, we, of course, urge caution in using free time from the internet, and advocate using a dedicated time server inside your firewall, on your network. Let's talk about that here for a second. And I want to talk about some security aspects on a time server, since they're a very popular target. Certainly you can do expected things like access control lists and authentication. But in particular, what I want to talk about is something that we call the security hardened NTP reflector. Okay, so what is a reflector? If you consider the blue box, again, being a time server, in this case it's a sync server, the NTP operations are going to be 100% in hardware via an FPGA. So any packet that comes in off the network goes immediately to this hardware. So consider the network. We have inbound NTP packets. They go into the sync server. They immediately meet the hardware interface, and that interface examines those packets. If it's not an NTP packet, it is immediately dropped. If it is an NTP packet, it's examined and it needs to be properly formed. Any malformed NTP packet is dropped. And so it's a very deterministic style, stateful device, hardware-based machine, if you will, built to respond at a very high rate of speed to NTP packets and effectively reject everything else. Now there's some nice advantages here, and let me go in to talk about how this is real beneficial in the context of cybersecurity as to why you would want or need a security hardened NTP reflector. And it comes in two reasons. One is the security of the device and the performance that you get out of it, because remember our ultimate goal here is to provide UTC time services to those servers, routers, cybersecurity systems that are working hard to protect the network. So when we look at the security aspects of it, a distributed denial of service NTP attack can't bring down the time server. It's not susceptible to any kind of reflection attack. A malformed packet is not going to disrupt the operation in any way, shape, or form. You look at the performance of a device like this, the timestamps are at 15 nanoseconds RMS, so that the world of NTP and log files, that would be basically perfect. Port-by-port packet limiting. Nice thing is a denial of service detection. So if the IT guy is expecting 1,000 packets per second and he's getting hit with 80,000 packets per second, he's going to get an alarm, let him know that something's underway. And it's quite powerful in terms of its packet processing. It can handle more than 120,000 packets a second. That's quite a bit. And the whole idea there is you can continue to provide time services to your clients that need it, as well as fend off a denial of service style attack. So when we look at sort of the end-to-end here, then you can see how GPS is this great, reliable UTC time reference, ubiquitous around the planet, right? On the other end, we have cybersecurity. It's a UTC time consumer. These time servers, such as the sync servers, sit in the gap and need to be defend against the various types of attack. And so you're going to want it to be hardened. And in our view, we're merging the best of, the timing and the networking technology into a single device with great accuracy, some GPS jamming protection in the form of an atomic oscillator, and then moving NTP into hardware, right? So it's very robust, and the reflector protects against the most prevalent cybersecurity attacks. So with that, I don't think we have questions. I think I hand it back to you, Alan. So thank you very much.
That's correct. Thank you, Paul. You've handily answered one of the questions that was in the queue. Someone had written in to say that, well, precise time, I'm not sure how that plays a key role in cybersecurity. Can you elucidate that? And which you have done very ably. So we will return to other questions submitted toward the end of the hour. Right now we're going to hear from James Curran at the European Space Agency, taking a system perspective on security. James?
Thank you, Alan. So I want to talk a little bit about kind of a system side view of it, that given all the problems that have been described so far, if we wanted to do something about it, or if the system was going to do something, what approach should be taken, what might be meaningful, what could we hope to achieve? So I don't need to introduce the idea that there are threats to GNSS. Whether or not they're actually growing, certainly the perception of threat is growing, and it's growing rapidly, and people want something done about it. And already we're starting to see, I guess, what you might call a bottom-up approach to pushing all our receivers in the direction of being secure. We're seeing augmentation, antenna arrays, inertial units, sensors, clever signal processing. We're equipping authorities with interference and RF detection units, and we're even getting the law in order to be able to deter potential adversaries. But on the flip side, if we were to try and tackle this from the system side, what should we do? Who do we want to serve? Who's the likely user? What do they want? What are the requirements? Can we even meet them? And if so, how should we do it? So they're kind of big questions, and they're actually quite unclear. Not least of all because there are very many users, potential users, and a very diverse set from cellular handsets, single frequency, low power, connected devices, automotive, maybe not connected, maybe no power constraints, multi-frequency, high precision receivers, maritime or agriculture, timing as we just heard. They're all very different. They have all different wants and needs and constraints. Probably a one-size-fits-all solution isn't going to nail it. So it's worth identifying exactly what do people want. Beyond doing that, you can probably start to subdivide it a little bit, even without a clear vision on requirements, and start to think about functionality in terms of groups of users who might use a service if it were there and how they would use it. I guess the first and most important group of users are the non-users, the people who are happy with GNSS the way it is today. Certainly, you don't want to degrade their user experience. But beyond that, there are kind of two different groups of users, and Logan spelled this out very, very nicely at the beginning. Those who inherently want to know where they are, the earnest user or maybe the self-spoofing user, where it's the receiver itself needs to know where it is, versus the reporting user who needs to justify to someone else where they were or when they were there. And it's an important distinction. So we can look into these two different classes and how you might address them with a signal design. But ultimately, we kind of have to acknowledge this is passive time of arrival ranging. It's never going to be perfectly secure, but we can get maybe some of the way there. So kind of given an idea of how we want, or how people might want to use signals, we can start to trace that through to specific functionality. So what is a secure GNSS? What we're really looking for is we want a secure PVT. And a PVT is kind of comprised of two parts, a set of ranges and a set of locations at the other end of those ranges, so where the satellites are. And that's two pieces of kind of information. One is a range and one is an ephemeris, so nav data and ranging. And there are two entities that need to be protected to be able to protect the PVT. And the nav data and the pseudo ranges are both used by a standalone user, but kind of only the ranging is used by this reporting user. This is the evidence case here. So if you imagine in the top right-hand picture, we've got a kind of self-spoofing user or an earnest user who's going to observe signal in space and process it and extract from that signal two things, a pseudo-range, which must be verified, and navigation data, which must be authenticated, and we'll combine them into a secure PVT. And the other case is the evidence kind of user who will observe the signal in space and simply report it to an authority. Interestingly, there's a nice problem there, is that one has to somehow link that data collected by the reporting user to the reporting unit itself. That's quite an interesting problem, but it's kind of out of the scope here. So that's kind of the functionality. We want to look at protecting data and protecting range. But that's not enough. Really, how well do we want to protect it? How do we want to protect it? And what are we willing to invest? So the real question is, what are the specific requirements? And this is a very vague and open question, and it's very hard to piece together what it might look like. If we were to define, I want to protect navigation data and I want to protect range, what do we really mean by that? So you can imagine if you gave this sheet of paper to a bunch of people and asked them to fill it out, you'd get a lot of different numbers back in all those places. And they all essentially define a different system, a different set of signals, a different scheme. And this is the real challenge, I think. We know we want something, but do we really know what it is we want? Okay, so imagining that we had defined how we want to protect data and how we want to protect range, what's the next step? The next step is somehow mapping that to a specific functionality. And this is where it kind of gets interesting. So protecting data. essentially that's a well-known problem, and that's been around for a long time. This is data authenticity or data origin authenticity. I mean, this directly maps to digital signature algorithms. So this is done. This is solved. We know how this is done. And we can just take an off-the-shelf solution. For example, as DSA or ECDSA. Without knowing it, you and I, we do this every day. Our cell phones, our computers, we do this all the time. The pseudo-range problem is a little more tricky because range isn't really a property of a signal. You can't just sign a range. You can't just certify a range. I mean, a range is a coincidence of two events, a transmission and a reception. So it doesn't really directly map to a cryptographic function that we can just take and use. Kind of the best we can do is render signals unobservable. We can obfuscate them. That might get us some of the way, but we can already see that this isn't really going to nail the problem at hand. So, as has been mentioned in Logan's talk at the beginning, what we might like to do is to try to somehow encrypt the signal. So conveniently, we can observe a correspondence between spreading, or bipodal multiplication, and addition over GF2. And we can say, oh, well, spreading code kind of looks in the reals just like encryption over GF2. Maybe we can just take a stream cipher. And it seems obvious, but this is kind of what we're doing. So we can say, oh, let's go and choose an off-the-shelf stream cipher. Maybe we could use something like that. The problem there is we're not necessarily making a signal difficult to forge. In fact, we hope that the user can forge it in order to do carrier wipe-off or code wipe-off. But we need some sense of asymmetry to make the signal safe. And this is where the concept of delay release comes in, as was already mentioned. That's an interesting point. It's a pseudo-asymmetry, but it does place an interesting requirement on the receiver, and that is time. We know the signal's safe if we captured it before this key was released, so we must know when this key was released, independently of GNSS. If we can do that, then this sounds like a workable solution. Okay, so it looks like we've kind of mapped a desire for security to a set of assets we want to protect, data and range, and kind of map those to a set of cryptographic functions that could kind of do this for us. So we're well on our way to looking at, oh, this might be a workable solution. So let's reassess. Is it practical? Would a scheme like this, or how would you assess if a scheme like this would be useful to a user? We have to look at what requirements we've imposed on a receiver. So for the data, we're thinking, oh, well, something like a digital signature might work. What does this impose on the receiver? The first thing is initialization. We need to somehow tell the receiver what the public key is. We need to give them a certificate. We can reasonably assume that this can be installed in firmware. We're imposing sensitivity requirements upon the receiver. They must extract a hell of a lot of data. It's not an easy task, given that many of our modern receivers don't have very good sensitivity. We're looking at, say, cell phone or GPS watches, which are typically hovering around the 40 dB hertz or lower, and navigating fine, but maybe it's going to be challenging for them to extract a lot of data. And also, interestingly, processing power. I mean, we think correlation is a hard job. It turns out that cryptography can be even harder. And you can see top right there, this is just a kind of processing time for ARM processors, Cortex M3, M4, at different processing speeds. And it looks like it's a pretty tough job. In terms of range protection, some other interesting requirements. The first is bandwidth. If we were to put a watermarking or some sort of encrypted signal, where would it go? Would it be falling within the bandwidth of a signal we're already processing? Would it be off somewhere else? Would all our users potentially see it? Where would we put it? How much bandwidth should we occupy? How much power should it occupy? Memory is important. We need to buffer samples. We want to process them post-mission. Sensitivity, of course, maybe if I have time I'll show later on. The kind of security we can expect is related to the sensitivity related to SNR. And again, processor, I mentioned, although with stream ciphers it's not so severe. And timing. And Logan mentioned it earlier, the delay release of a key. This is actually important. And has implications for when the receiver is very uncertain, cold start, factory reset, or power cycling. There's one other little detail. It's not so obvious. It's what you might ask the community to do. And this is perhaps relevant, perhaps not. We're notoriously bad at implementing crypto. And we hear it all the time. There's some news, some new big breach, some new bug has been discovered. And some of the best programmers in the world have messed this up. And it's usually not the algorithms at fault. It's usually the implementation. And as an example, top right, the last 5 years, 83% of vulnerabilities in security have been traced back to poorly implemented protocol, when there was nothing wrong with the protocol itself. Famously, the Apple Go-To fail was one line of code which rendered everything insecure, and similarly, 2 years previous was the famous Heartbleed scandal, where it turned out that everyone's server was insecure. So there's a good argument to be made that although off-the-shelf algorithms mightn't be perfectly suited to GNSS, it's probably best to play it safe and take something that we know works. And ultimately then we have to look at it and say, okay, when we have all these pieces in place, we do have to acknowledge it's not going to be perfect. For the data, we can say we take an off-the-shelf solution, we know we can enjoy provable security, we can provably assert that our data is secure from being changed, but that's all. From range, we've already acknowledged, well, this isn't a perfect solution. It's not a one-to-one mapping between securing a range and encrypting a signal, but it's pretty strong, and we can eliminate a lot of threats. However, to have a secure PVT, we need to both secure the ephemerides and the range. And so far, we can only confidently do one of these. Now, I was going to briefly mention a few other points to support these claims, but looking at the time, I might skip right to where I was going. And say, GNSS, ultimately we're looking at a channel estimation problem. And we're trying to estimate the channel from the SV to the user. And we make a lot of assumptions in doing this. Really, with a signal, you can only secure assets that are present within the signal. And that's only the data. Everything else, we can just enable receiver-based techniques. We can make challenges more difficult and we can make defense more easy. You can't really reach out and secure a range. So we have a partial result. It's still a statistical game. It's still a power and estimation game. It's looking for power and noise. And that's not quite provably secure. So we're always going to need some sort of receiver-side defenses. So we need to look at defending both ends of the range, at the satellite and at the receiver. Beyond that, once you put together a working concept, it looks like it's going to be very important to put it in silicon and put it on the bench and try it. Some rather curious results come out, some obvious, some not. We can see very clearly that receiver vulnerability is proportional to uncertainty. And so really our important critical test cases are cold start and forced reset conditions. Also have to think about uptake in the market. We really have to consider, is it easy to implement this? We've got 10, 20 years of optimizing signal processing algorithms for GNSS, but maybe not so much in the crypto domain. Maybe a GPS watch isn't quite ready for this. And beyond that, there seems to be a good, strong justification for taking a working solution and trying to use it in our case. Okay, so I've kind of rushed the end of that, but hopefully I brought everyone along with the story. And back to you, Alan.
All right, thanks very much, James, and we appreciate you skipped over some rather valuable material, but there's so much to present, and we have a limited time. We're going to go directly to Andrei Soloviev from QNAV, who's going to, there we go. He's going to talk about signal processing and sensor fusion. Andrei?
All right, thank you, Alan. So I'm going to follow, in a sense, James' talk and really look at what can be done on the receiver side to protect, essentially against not so much cyber attack, but more RF type of attacks. And I'm not really going to give you a final answer, so this is the approach we're going to use because it's a fairly active area of research. So we're really going to outline different methods at a relatively high level that can be fairly efficient for protecting against RF type of attacks at the signal processing and sensor fusion level. Before we're actually going to dive into, so I'm going to talk about the full-level protection scheme and benefits of sensor fusion, and also provide an example of limitation of a deep GPS inertial integration for interference suppression, which is efficient against both spoofing and jamming as well. But before I'm going to dive into specific methods and specific algorithms, I'm going to quickly remind the overall GNSS receiver architecture at a very high level, because really protection levels, they originate from this architecture. So what we have here is the GNSS antenna and the RF front end that downsamples received signal, and then there's a signal processing part, correlators and loop filter of some sort. But essentially the goal of the signal processing part is to accumulate the signal power as much as we can while suppressing noise, interfering, and jamming signals. The signal processing component provides GNSS measurements, pseudo ranges, Doppler, and carrier phase, and navigation data. And this is used by the navigation estimation part to compute position and timing solution. So essentially, when we get the signal from the antenna all the way to the navigation solution, there are 4 different levels we can look at and implement some protection measures at 4 different levels. So there's a pre-correlation level, really working with signal samples. So the most popular approach, and pretty much the only thing you can do at this level, is to monitor power levels of signal power and or noise power. So if there's anything anomalous going on there, that's generally an indicative of an attack. Then there's a correlation level, probably one of the most interesting protection algorithms. They work at the correlation level. I'll give you some examples later on. But essentially, when you observe multiple peaks at the delayed Doppler correlation space, that is generally an indication that there's something wrong. When the spoofing signal is overlapped over the direct signal, there's some distortions in the autocorrelation function. Most efficiently, they can be monitored by what is called a chip-shape correlation approach. Now, at the measurement level, receiver autonomous integrity monitoring techniques can be still applied, especially when we incorporate carrier phase into the picture. That becomes most sensitive for identifying and excluding potential malicious signals. And finally, at the position level, at the solution level, the first thing is a relatively simple thing to do is the cross-check. When you have multiple GNSS systems in place, then you can cross-check position solution or velocity and timing solution from multiple constellations. It's unlikely that a spoofing attack is going to be mounted against various constellations, so it's just more difficult to do it. So the cross-check is a fairly straightforward approach. Also, you can monitor your clock solution and identify if there are any deviations in normal clock behavior. That is generally an indication that something's wrong there. I'll give you an example later on of how it works. So in terms of the pre-correlation level protection, this is an example, and the data I'm showing was generated by the University of Texas at Austin, Todd Humphreys and his group. This is publicly available text data files that you can download and use for verifying your spoofing protection algorithms. So the way that the pre-correlation method works here, we're actually looking at the signal-to-noise power ratio. And initially, they're only open sky signals, direct satellite signals. But then spoofing signals are introduced, and as a result, the overall signal power jumps while the noise power remains the same. So the monitor identifies this jump and raises the spoofing detection flag. It doesn't do anything about spoofing, but it tells you, the receiver, that the spoofing is present, and you don't want to trust your solution at this point. So the correlation level protection are really based on the fact that the spoofing signal cannot suppress the direct signal. So it tries to fool the receiver, but it cannot really take out the direct signal from the picture. So we're looking at the correlation space here, signal energy versus Doppler versus the code phase. And when the spoofing signal is introduced, generally there are 2 energy peaks. So this is abnormal situation. When there's only direct signal present, there's only 1 peak that we're observing. The 2 peaks, something's going on there. So this is a real-life example on this slide here. Not a spoofing. It's sort of an unintentional spoofing. The strong multipath in urban environments reflected from a building. But what we see here in this in the slide, in the right, lower right part of the slide, the image, it's an actual image of the GPS signal in the correlation space, delayed Doppler correlation space. And there are two peaks in there. One is due to the direct signal, another one is due to multipath. So when the multipath again here is sort of an unintentional repeater or nicomer. So when we look at the correlation domain space, we clearly see two peaks, which identifies that there's something wrong in this picture here. So at the solution level, you can do cross-checks, monitoring clock estimates can be actually very efficient for identifying spoofing attacks. So what's going on here is essentially we estimate the clock drift from carrier phase, and deviations in the clock behavior are due to the fact that spoofer may be pulling our timing solution, or it's trying to pull our trajectory from its desired path, and the difference in the trajectory projects into the clock behavior. But we see some significant deviations, and especially when the carrier phase is used to estimate the clock drift, even decimeter type of deviations can tell us that there's something going wrong with the receiver. So it can be used for identifying the spoofing attacks. So to summarize this part of the discussion, really we're looking at the protection at 4 different levels. And there's not a single algorithm or signal protection level that can just solve all the problems and address all the issues. Some of them are efficient against certain types of attacks, while others are efficient against other types of attacks. For example, pre-correlation level protection works with relatively strong interference signals, while the correlation level protection is really most efficient where the spoofing signal power and the direct signal power are comparable to each other. So really, to maximize the benefits, we want to combine all these 4 different methods and use the features and beneficial features all together at the same architecture for protection against RF types of attacks. Another very powerful thing that you can do is to integrate GNSS with other sensors, especially when we integrate with inertial navigation system. It's a self-contained system, so you cannot spoof it, basically based on measuring physical forces and integrate them into navigation outputs. So it's completely self-contained. So the way it works, you have your measurements from a GNSS receiver. You can predict what this measurement should look like based on the inertial navigation, and then cross-compare the two. So a significant deviation present there, then just don't trust your GNSS receiver measurements. If the cross-check is good, then the common filter, the GNSS inertial common filter, takes verified GNSS measurements and use them to reduce drift in inertial navigation outputs. The benefits of sensor fusion are maximized when integration is done at the signal processing level, when inertial is used to aid the GNSS signal processing part and suppress interference signals as much as possible. And deep integration is one example of the integration of fusion, GNSS, and inertial at the signal processing level. So the example I'm using here, the deeply integrated implementation uses long coherent integration of satellite signals to suppress jamming and interference. So we integrate coherently over 1 second. So again, the idea here is fairly straightforward. We just accumulate the incoming signals for as much as we can, while suppressing any type of interference for as much as we can as well. Coherent integration enables maintaining a complete tracking status, including pseudoranges, Doppler, carrier phase, and the data bit decoding. So you can do all the 4-level spoofing protection methods when this technique is applied, including RAIN. It's mostly efficient against jamming. It's helpful against spoofing, but really the sensor fusion implementation with deeply coupling of GNSS and inertial provides you some very significant benefits for jamming suppression. A 17 to 20 dB increase in the signal tracking margin as compared to a standalone unaided receiver. So just a quick results here on the slide, the tracking of the carrier phase at a 70 dB jamming to signal power ratio using P-code data simulated, generated by the Spirent simulator, again maintaining the precise tracking of the carrier phase. So just some really high-level takeaway points from my talk are really GNSS receiver architecture can and should be protected at various levels, and we really need to look at 4 levels of protection to maximize the benefits. Sensor fusion provides significant benefits, specifically through the cross-check and integration at the signal processing level. And this is all I have, and hopefully we can elaborate on it a little bit more during the Q&A session. Back to you, Alan.
Thank you, Andre. Yeah, you started in a direction, sensor fusion, that we are going to return to in our first question, or in a sense, or explore further. One of the attendees wrote in, what are your feelings toward GNSS alternatives, for example, ELA-RAN or others, as a backup in case of failures, or in what we're specifically talking about, in the case of cyber attack? And I'll throw that question open to anyone on the panel who wants to speak, and we'll hear from anyone who wishes.
Well, this is Logan. I guess I would argue that anytime you're trying to verify and validate positions, it's almost like a detective trying to interview a bunch of witnesses with varying reliability. And so I would argue that ELA-RAN is another witness, and it's one that's very difficult to interfere with. And so it would be an extremely reliable witness, particularly with regards to time.
Yeah, this is Paul. I would agree. The one thing about a GPS timing receiver is generally it is stationary. And so to Logan's point, you can have one reference being GPS or GNSS that gives you an idea of where you are, and you can cross-reference that against another one. And the two should match and should never change since the unit is not generally moving.
All right, thanks. A second question comes in, and this calls for prediction or opinion, and prediction is difficult, as we know, particularly when involving the future. But one person wants to know, what is the likelihood that GPS spoofing will actually become more prevalent? Jamming seems more likely and a more effective threat to localized GNSS equipment. Can you differentiate between spoofing and jamming, both in terms of protective approaches and likelihood and counteractive measures? Anyone?
Well, this is Logan again. Oh, I was just going to say that there's increasing motive and there's increasing means, and when you put those two together, that's pointing towards increased likelihood of spoofing. And one of the attractions of spoofing is that it does not necessarily raise an alarm. If somebody jams, there's going to be an alarm. And so I'm going to take the example of the guy in New Jersey who was jamming the airport back in 2012. He used a jammer, and I would argue that an intelligent receiver should have been able to detect that jammer, and he may not have been able to communicate back to the base because it was jamming the other signals as well. But if that receiver had been logging the fact that it had been jammed for the last 5 hours, and when it finally did get back into a coverage area, say back at the home base, there probably would have been a discussion with Gary, basically saying, Gary, I notice you're jamming my GPS unit. I'd like that to stop. And so that is an effective countermeasure. Now contrast that with a spoofing attack. And again, these can be cyber attacks. There would be no such warning. And in fact, in the phishing industry, spoofing of AIS systems is becoming fairly common in a lot of phishing waters. So yes, I would argue that spoofing is going to become more prevalent, mainly because there's motive and there's means.
I might add to that, if I may. I don't think it's so black and white. When we talk about jamming, this is a very primitive device. We're talking about injecting lots and lots of power to RF and drowning out everything else. And when we think of spoofing, we think of a very sophisticated device, and kind of our mind jumps straight to a spar and simulator. And there's no reason to assume that there's nothing in between. There's no reason to assume that once we have our receivers equipped to detect jamming, that the jammer doesn't just get a little bit smarter and does a little bit of synchronization, some tiny, minuscule added complexity just to get around the detection mechanism. It's about jamming without being caught. And as soon as the motive is there, we're not going to be motivated to go from a CW jammer all the way to a simulator. The adversary will be motivated to do just enough. So what I would imagine will happen is once it becomes a problem, we'll start to see incrementally more sophisticated attacks, maybe just targeting little bits of the nav data, just enough to knock the receiver out of track, not necessarily a foghorn of a CW wave.
Yeah, this is Paul. Let me just add to that. I agree as we go forward, we can expect things to probably be more sophisticated, but in the context of today, jammers are very prevalent. They're easy to obtain. You can buy them off the internet. And as it relates to cybersecurity, as soon as a jammer goes on and a receiver, like on a time server, loses lock, it creates a log file entry, right, which is going to assist in the cybersecurity efforts. In the case of the airport, of course, if they had, for example, an atomic clock in their time server, let's say, they would continue to get accurate time services, and then the logs of the jammer, or the GPS, if you will, coming and going would provide evidence that, you know, there's something happening for a very short duration as the guy drove by in his van, and it would kind of give you an idea when to go look for them. So it kind of points to the importance of logs and timestamps in the logs, as well as, you know, a mechanism to continue to deliver the time services while being jammed.
Yeah, this is Andre. I just wanted to quickly answer this. So I think really jamming versus spoofing really depends on the application. Really, as Logan and James were referring to, I think the jammers, you know, they're very simple jammers that can be implemented. Spoofing is a much more sophisticated type of attack. But for self-driving car, it's hard for me to imagine that somebody would like to spoof it. When it comes to critical infrastructure, then it becomes a different picture. So I think what we can do on the receiver side is to design the protection mechanism and put the protection mechanism in place such that it becomes more and more difficult to generate successful spoofing attack. And then maybe there's just no sense to spoof. There's just too much effort for what's out there.
All right, thank you, everyone. We've reached the top of the hour, but we have a couple more questions still, and we are going to extend for just a few more minutes. Audience is holding steady. Thank you, all of you out there, for your attention. Couple of final questions that may pertain more to Paul, but anyone else who has an opinion or perspective, jump in on it. One question. What specific protections are being implemented in timing receivers to mitigate attacks on GPS equipment?
Yeah, so I think I pretty much mentioned the jamming part and having an atomic oscillator. Another protection actually relates to NTP, since the device is stationary, so you don't expect the position to be changing. NTP itself, it's always a very good practice to peer to other time servers and other locales that may not be experiencing the same event. There's certain peering clustering selection algorithms that are there to detect false stickers. So if the time is being dragged off by your GPS receiver unwittingly, the NTP daemon can actually begin to detect if there is a change, and can, in fact, if it gets dragged off far enough, even reject the time from the GPS receiver. So there's some good best practices in there that certainly use the time from GNSS, but cautiously internally monitor it as well.
Finally, and this could be the subject of a webinar all unto itself, so I'll ask you, Paul, to give us a capsule description. One person wants to know, do you think NTP, Network Time Protocol, will eventually be replaced by PTP, Precision Time Protocol? And if you could just briefly sketch the differences and what the future is likely to bring.
Yeah, that's a really good question. And you have to put it in context, is this for the next 5 years or is this 25 years from now? Both of them have advantages. If I take NTP, for example, not only is it a timestamp exchange that has some authentication capabilities and so forth, it also has various peering clustering, clock steering, selection algorithms, where the daemon actually steers the clock and looks at other clocks and makes measurements to make sure that it's keeping the best possible time. And so there's a lot of technology that's been put in NTP over the years to really make it a robust timestamp exchange and clock steering protocol. So there's a lot to be said for that. Another thing is it is pretty easy to implement. If I look at PTP, PTP is a mechanism to exchange timestamps very accurately at very high rates so that you can achieve a much closer, tighter synchronization between a master and a slave. It very much leverages hardware timestamps, and it's being rolled out, certainly in Grand Masters. It's being rolled out in what we call on-path support in routers and switches. And the timestamping capabilities are showing up in servers. And so with all of this time transfer technique available, you can see PTP growing, out of power and enterprise, power and telco, for example, and getting broader adoption in the enterprise space. But the thing to remember is that PTP does not have the clock steering algorithms and a lot of the math and science, so to speak, to keep a clock real accurate. That still is large in the domain of the implementer of the PTP slave. And since that's the case, it becomes more of an engineered solution and a little more work right now and a little more money to implement PTP. But if you need the accuracy, like is the case in a number of different applications today, PTP is a great solution to give you that the time accuracy. It's a good mechanism to transfer the time accurately over a network to steer a slave clock. So it's frankly going to be a very interesting decade, if you will, as we see these technologies roll out and find their niche applications. And certainly from our perspective, looking at PTP is very exciting, is what's happening in that realm as well.
Thanks, Paul. Any comment on the timing aspects from other members of the panel? Well, we have now reached the end of our time. I want to thank all of our speakers and our sponsor, Microsemi, for this fascinating look at cybersecurity. We've covered a lot of ground very quickly. And if you didn't get a chance to fully take it all in, this webinar will be posted within about 24 hours. I think Joelle will return and tell us exactly when and where. The webinar will be available for you to review over the next 6 months to a year, also to share with colleagues. Anyone can sign up, register, and be able to listen to the recorded form of the webinar and view the slides as well. I'm Alan Cameron from GPS World Magazine. I want to thank our speakers, Logan Scott, Paul Skoog, James Curran, and Andrei Soloviev. You can see everyone's emails there on your screen if you have a particular question about their expertise, and we will return with some of these questions, perhaps in a printed or e-newsletter form, and our panelists' answers. So look for those in the future. Again, I want to thank Microsemi for sponsoring this webinar and turn it back to Joelle.
Like Alan said, thank you everyone for attending the GPS World webinar sponsored by Microsemi. A recording of this webinar will be emailed to you tomorrow and posted to gpsworld.com/webinars. That will be available for use up to 1 year. Upcoming webinars from GPS World also will be posted to that page. So thanks for attending, and we hope you'll join us for another great webinar in the future.